Yesterday we talked about different shielding gases. We had talked about helium the day before, but I talked about diatomic hydrogen and how it has a reactive thermal conductivity. Basically, in the body of the arc, you break down the diatomic hydrogen into monatomic hydrogen, and down here in the boundary layer, it recombines. So you have a heat of dissociation being put into the hydrogen here, and it gives up that heat of dissociation as it recombines, or sometimes called the heat of recombination. And that effectively transfers extra heat to the surface. And so hydrogen, small amounts of hydrogen can make big differences in the thermal conductivity and the heat transfer across the boundary layer and the size of the weld pool that you melt. In fact, an early type of welding torch was called the atomic hydrogen torch. And it was basically just two electrodes coming in like this. And you used hydrogen gas, and you dissociated the hydrogen, and you got a flame, and it basically it's hotter than your typical oxyacetylene flame, the atomic hydrogen flame, because of this reactive thermal conductivity that comes into it. So you can, with an atomic hydrogen torch, you can probably get 2,000 watts per square centimeter from a flame. But in this case, you're not running current into the workpiece. You're just running it across two electrodes and getting a jet. We'll talk about plasma jets in a second. Getting a jet flame of hot hydrogen, but it's atomic hydrogen, and as it recombines, you're getting extra heat transfer. In fact, I guess an atomic hydrogen torch, I've never seen the data, but you might get 3,000 watts per square centimeter. So you can get a very intense flame without carrying electric current with an atomic hydrogen torch. I've seen pictures of them in books, and I think I actually saw one when I took over the lab. There was this thing, it looked like it was a bunch of rods and wires, and it was stuck away in a cabinet. I think we finally threw it out, but I think that was actually an atomic hydrogen torch. They really haven't used them for about 60 or 70 years. We talked about arc ignition and how it occurs by touch start, just gently touching the surface and bringing it apart. As you pull those two surfaces apart, you can actually vaporize a little bit of metal. As you vaporize the metal, you get to temperatures with voltages of less than a few volts, certainly less than 5 volts. You can get temperatures sufficient to ionize some of the gas. And that's how touch starting works. The other thing we talked about at the very end was high frequency overlay. Basically, you have you introduce a high frequency into your several hundred amp circuit, which is not the easiest thing to do. It's basically they have a spark gap. If you look at the welding power supplies, the old transformer rectifier power supplies, you actually had a little arc gap inside the machine where you generate an arc and you'd have a magnetic field to give it a little high frequency. And you turn that thing on and the radio would go buzzing away, right? Because you got all kinds of radio interference. Nowadays we have we can get high frequency basically because we use inverter power supplies, which is a high frequency type of transformer system, if you will. But the high frequency is particularly helpful on aluminum. Sometimes you run it continuously. Sometimes in many power supplies, it'll have a switch and it'll say high frequency on at the beginning. It'll have a little knob, so you have it on for the first 3 seconds of the arc or the first 5 seconds. Others, and they also have a switch position where you run it continuously. So if you have a particularly dirty aluminum or something and you have a problem with the arc going out because of the refractory aluminum oxide, just leave it on all the time and it helps restart the arc for you. This is, anyone came in late, that's where you can find the lectures in the next few days. And those are the passwords and login. Okay, so that's two of the things we covered yesterday. There's another point that was kind of in here with arc ignition, and that is don't believe everything you read in handbooks. One of the great lessons about that you learn at the culture of MIT is that, as Professor Shine over the Sloan Schools used to say, MIT is an iconoclastic society. Anyone know what an iconoclast is? It comes from the Greek icon, meaning image, and clast, which is the root for break. We break down images of things that are already there. An iconoclast is someone who's always taking shots, okay, at things. And if you haven't realized that yet at MIT, you should by now, right? We're very critical both of ourselves and other people, and ideas. Now, hopefully we're not critical of the people, but we're critical of the ideas. And we don't always believe everything we read. Now, I actually have a kind of a corollary to that. MIT has a culture of creativity because we don't only just break down things, we actually try to put something else back in its place, at least from a scientific point of view. Okay, we try to, we're critical. You have to learn to be critical of things, and there are all kinds of things in the welding handbook that are just flat out wrong. There's all kinds of things in the scientific literature that are just flat out wrong. If you take the World Trade Center, it wasn't since yesterday I looked on the web on the AP, and they're still talking about the steel melting. It's impossible, and we've now talked about pre-mixed flames. It's impossible to melt that steel in that flame. And let me just kind of give you what you should know now. You should be able to do the calculation. If you know that the adiabatic flame temperature of a hydrocarbon burning in air, or in, I'm sure, in pure oxygen, is about 3,000 degrees centigrade, right? I mean, it's like 2,800, I said, for MAP gas, 2,870, 2,900 for MAP gas, and for acetylene, it's like 3,100 or something like that. So that's roughly the adiabatic flame temperature. And just look at it. If I've got 4 moles of nitrogen plus 1 mole of oxygen, which is basically air, right? Plus some hydrocarbon going to carbon monoxide plus hydrogen, and you can say, well, you know, it depends on what hydrocarbon I have. It's CXHY, right? Well, obviously this would be XCO plus Y over 2 H2O. But it turns out most of the hydrocarbons have about twice as much hydrogen as carbon. Polyethylene is almost exactly that, except for 2 hydrogens on the end. So for every mole of oxygen, I get approximately 1 CO and 1 H2O. Plus, I still carry through the inerts. So I have the reaction of from burning 2 moles of gas, but it has to heat up 6 moles of gas, right? 1, 2, plus 4 is 6. So instead I would have ordinarily heated up 2 moles of gas in a pure oxygen flame with no inerts. Now I have to heat up 6 moles of gas. What's the temperature here? What's the adiabatic flame temperature approximately for a gas burning in air, the same gas burning in air? It's 1/3, right? As much, because I got to heat up 3 times as many moles of gas, right? So the adiabatic flame temperature is about 1,000 degrees C or 1,800 degrees F. (1832) if you want to be exact, right? But I'm not, you know, I go to 1 or 2 significant figures, sometimes half a significant figure. What is half a significant figure? Anybody know? Half a significant figure, if you're in a geometric system, is within a factor of 3, right? Because the log of a half is 3, right? Or 0.3, or whatever. Anyway, so sometimes I deal with half a significant figure, order of magnitude. Within half an order of magnitude is a factor of 3. So the maximum temperature is 1,800 degrees F. That's nowhere near the 2,600 degrees F of the melting temperature of steel. And this would be for a pre-mixed flame. I didn't have pre-mixed flames, I had diffuse flames. And not only that, at the World Trade Center, anybody see the black smoke coming off? What's in the black smoke? Fuel. And so I got extra moles of fuel in that flame. So the actual temperature is probably down around 1,400 degrees F, or something like that. And that you just get kind of from experience, because I had extra moles of fuel. It was definitely a fuel-rich fire. You know, 24,000 gallons of jet fuel on a couple of floors makes it a fuel-rich fire. You got black smoke, which tells me it's a fuel-rich fire, and we also know that most diffuse flames are large diffuse flames are oxygen-starved because you blow on them and they get bigger, right? So you know all that now, and so You learn in this class how to analyze, you know, a stupid statement like the steel melted. Okay, it's actually not a stupid statement. It's kind of what the layperson hears. But I'm hearing this from all kinds of scientists, okay, who are saying this, and they haven't even stopped to think about it. They haven't stopped to even try to be quantitative. And if there's anything else, hopefully you can get out of this course, is it's not that hard to be quantitative. You don't have to be fancy. It's high school algebra type of things. You have to know some of the physical principles, and you do have to kind of know some things, like not everybody knows the adiabatic flame temperature of a hydrocarbon is 3,000 centigrade, but now you know some of these things, right? And I've done the same types of things on simple little economic analyses as well. So, okay, so there was more to arc ignition than just slamming the welding handbook. Oh, well, at 1200 F, the steel loses half of its yield strength. Okay, so the steel did soften. I mean, that's we stress relieve steel at 1200 Fahrenheit. Okay, we talked about stress relief, and basically you're just lowering the yield strength. In fact, I think I drew that diagram the other day. Okay, so if I drop the yield strength by a factor of 2, but the other problem at the World Trade Center, it's not uniform temperature, you know. And so I've got distortions going on, right? And we've talked about, I can get yield level residual stresses with a 300 degree Fahrenheit difference in temperature, because the thermal expansion coefficient for a piece of steel is not 300 Fahrenheit, it's about 300 centigrade. So you're talking 500, okay? I can get yield level residual stresses because the thermal expansion coefficient for steel is 10 to the minus 5 per degree C. Well, 10 to the minus 5 times 200 degrees C is 0.002 strain, which is getting up towards the yield point. Okay, it's about 60 KSI, 67 KSI. Well, 67 KSI in something that's only got half the yield strength, 30 KSI, is obviously going to distort and deform. So I can have 200. I can have. All I have to have is a 350 degree temperature or 360 degree temperature difference on the floor. Can't you imagine that you had that from one spot to another? And you have these big long beams. And so I'm going to get significant distortion. And the reason I need that is if you actually watch the World Trade Center tape, and I did, it's pretty dull, I agree. But nonetheless, they pointed out that the design stress of the steel was about 30 KSI, but that's for a 140 mile an hour hurricane. The actual stress at the time, since it wasn't a windy day, on that steel was about 10 KSI. So what do I have? I have a factor of 5 or 6 safety factor. So just explaining the strength of the steel going down by a factor of 2 doesn't explain the collapse. I have to have something else, which is all the distortion and buckling. Now I've got structures that are no longer straight, like the designers intended, and I can easily get buckling stresses, right? I can get, you know, that, and if I drop my yield strength by 2, and I now have all kinds of distortions in there, then it's easy to see I can get a factor of 4 or 5 or 6 increased stress, which causes the things just to come down, right? I mean, you know, you can run the numbers. It's not that hard. You can do it in your head and impress your friends. If you have those kind of friends, you should get new friends. Okay. Okay, let's talk a little bit more about arcs before we go into heat transfer. There is something that's very important in an arc. I told you an arc is an electrically augmented flame, and we talked about a flame essentially burning and reacting and heating up the gas, and the expansion of the gas causes the gas to accelerate towards the surface, and you have a burning velocity in a regular flame. It turns out you have the same thing in an arc. I have cold gases coming in. They get heated to 10,000 Kelvin. That's a 300-fold increase in their volume, and you expect them to accelerate down. But in fact, they do kind of accelerate down and form this bell-shaped curve because I have a boundary layer down here. The gases come down and shoot off to the side. Okay, I don't want to put too many arrows on here, but it's the shooting off to the side that causes the bell shape to the typical welding arc. Now, it turns out there's something even more powerful than just that 300-fold expansion. That 300-fold expansion, if you run some typical numbers, might give you something on the order of a meter or a few meters per second as a velocity. Now, a meter per second is, let's say, a meter per second is 3 feet per second. That's, 10 miles an hour. I don't know, something like that. 88 feet per second is 60 miles an hour. You can figure it out. But that's not terribly fast. What happens is I actually have electromagnetic forces in this arc because I have a current, which I talk as a current density J, not as a current I, which is the total current, the integrated current, but the current density, amps per square centimeter, J. And the current is coming this way. That current has its own self-magnetic field B, and it's, oops, I got B going the wrong way. Right-hand rule, B goes that way, right? If the current's going down, B's going clockwise from the top. So it generates its own self-magnetic field. Have you ever seen what happens if I have two wires parallel with each other and they have the same current? They have the current going the same way, they're going to want to pull together. If they have opposite, they will repel. But in any case, it's just force is J cross B, one of Maxwell's equations in the integral form. And we have an axial component, a circumferential component. It's a vector cross product. And so the force is radial. And the force is radial inward. And it turns out, where's the current density the highest? If I have constant current flowing through this thing and the current is diverging, obviously the highest J is up here where the area is smallest, right? So I have big forces up here. I have small forces down here, smaller forces. They're all directed radially inward. Well, if I have a radially inward directed force, that's nothing more than a pressure, right? And if the pressure is high here and low here, that's a pressure gradient. And if I have a fluid and a pressure gradient, what happens? Flow. Things move. So what happens is I get a jet shooting at the surface at something on the order of 100 to 500 meters per second. This would be supersonic if it were room temperature. It's not room temperature, it's rarefied by 300 times, so it's not supersonic. But this 100 or a couple hundred meters per second is above the Mach speed. Okay? In fact, what is Mach? At STP, atmosphere, or at sea level. Don't remember that little constant? 343.6 meters per second. Does that sound about right? 1,000 feet per second is how fast sound travels. So to go 10 feet takes a 100th of a second for sound to go. Anyway, so, and you can count, if you remember the rule of thumb, if you see the lightning and then you count the number of seconds until you hear the sound, that's how many thousands of feet away the lightning is. Anyway, so anything above 343, if it was at room temperature and atmospheric sea level pressure, would be supersonic. It's not supersonic. We don't break the sound barrier here. However, it is a relatively intense jet. And those plasma jets are important for a number of reasons. One of which is that they control, in higher current arcs, they control the penetration of the weld pool. If I look at a low current weld pool, this is up to 150 amps. Arms are up to, let's say, 200 amps. And then I look at above 250 amps. I'll get two different well pools. This one's going to be very shallow. There will be about a half to 1 millimeter of surface depression from the arc. It's a relatively soft arc. That's what we call it. This one will have a very strong plasma jet, and I can have 4 to 5 millimeters of surface depression. The final weld here the final weld, after it's solidified and the thing is pushed by, sometimes looks like this. Because I actually, in the center, I've shown it like this, but sometimes it digs in like that, okay? Whereas the well pool over here, the well pool shape, when you're all done, it's going to be a narrow, shallow weld here. Because I don't have enough arc force over here, I may only be about 100 meters per second. Somewhere in this transition region, around 240 amps or so, you go to a very deep penetration. And it can be almost as I've shown it there. Here you'll end up with a well pool that may have a depth to width ratio of a third, a quarter. The maximum you can get is about a half. Over here you can get a depth to width ratio that's 1 or even 2. And in fact, for those of you in 3371 yesterday when I talked heavy section welding of titanium, this is what you do when you get to those gas tungsten arcs at 1,000 amps. You're essentially drilling a hole into the surface. And what happens is the metal flows around behind. Now, how many people have ever been in a motorboat going down in a lake or the ocean? You look at the wake behind you. What's the motorboat? The hull is basically pushing a depression into the surface of the water and moving forward. You have a similar type of flow behind the well pool. When you get a deep depression like this, it's like moving a boat through the water with a lot of draft deep in the water fairly rapidly. You'll get a flow around behind, and what happens, the water has to speed up to get around, right? As it speeds up, it comes back with more momentum, and it comes back behind, and it kind of comes towards the center. If you look in the back, you actually see a hump, okay, because of Bernoulli. He says that 1/2 mv squared turns into rho gh, and you actually get a rise in the wake, and then you'll see how the wake, pushes off to the side. I thought you were in the Navy. Huh? I'm not talking about big ships. I'm talking about going 30 miles an hour in a motorboat. Water skiing, right? The wake behind. Just think, next time you're in a motorboat, look at the wake. You have something similar in a well pool at these high currents. Now think about this whole thing solidifying as you do it. I can freeze in all kinds of defects when I get to these higher current wells if I'm not careful. Over here, it's going within the legal limit as you're coming into the bay or into the dock, right? You're less than 20 miles an hour type of thing, or less than 10 miles an hour. Not much wake, a lot more gentle. Not as much problems with solidification and defects. You get above 250 amps, start getting what we call humping, tunnel bead, and I should have brought, I actually had some pictures of it downstairs. But humping, you've seen humping in that movie from the British Welding, or the Japan Welding Research Institute on laser and electron beam, and you get these blobs of metal solidifying behind. I'll bring hump bead tomorrow. But there's lots of different types of defects that are caused because of that. In addition, the high velocity of this arc gives me more arc stiffness. I can have a problem if I'm welding outdoors and the wind comes by. If I have more than a 5 mile an hour wind, I can actually start blowing out the arc. If I have a 10 or 20 mile an hour wind, I can blow out the arc just like I blow out a candle. Just like Renaudot blows out oil fires. If you have a big crosswind, you can blow the plasma gas away and lose your arc. If it's not quite that bad, you'll get an unstable arc wandering off to the side, and the guy ends up not being able to control the arc and making a bad weld. That's why on a windy day you have to build a tent around the welding operation to keep the wind out. Okay? Now, you can also use higher currents, which will give you more stiffness to that arc. You know, you have more momentum going down, it takes more momentum going crossways to blow it up. It turns out on welding power supplies, if you look at this whole thing, since the magnitude of the self-magnetic field B is proportional to J, the magnitude of the force in that jet is proportional to the current squared. And so, it turns out the average welding power supply in the old days, when you had a transformer rectifier system, if this is time and this is current, it says DC, and it may say that you've got 200 amps DC, but in fact, you've got a ripple on there that's about plus or minus 30%. It's a huge ripple. And they leave it in intentionally, because if the power is related to the average current, but the arc stiffness is related to the average current squared. And so the stiffness goes up if I square the sine wave compared to if it was just a straight, flat constant, right? The square of this number is more than twice the square of that number, okay? So on some power supplies, you actually see a little knob that'll say arc stiffness control. And all it is you're taking some of the filtering out of the thing. If you filter this power supply, you can reduce this. You take the filtering out, and you go back to a lot of ripple. So they actually intentionally introduce ripple into welding power supplies to help control the arc and give it more stiffness. Another thing you can do is you can change if you're doing flux shielded welding, if you change the composition of your flux and you have things like barium or lithium and things like that, things in columns 1 and 2 of the periodic table, you can get a much sharper cathode spot. Or actually, that's going to be the anode spot, cathode spot. Anyway, you can change the arc characteristics and essentially get stronger plasma jets, because it's a question of the strength of the plasma jet is proportional to how much it diverges. The pressure differential, okay, you get a greater pressure differential if you get more divergence to the current. And by changing some of these easily ionized elements, you can change the rate at which the arc spreads out. You can change the width of the bell, if you will. And changing that can significantly change the stiffness of the arc. And in fact, I've just been looking at some things for some people in the last 2 weeks. There are electrodes that you should be very wary of using, called inner shield electrodes, which you don't have to carry an argon bottle with, because in order to keep the porosity out of the steel, remember I said if you welded with a bare steel wire, you'd end up with Swiss cheese because of the nitrogen in the air. Well, in the late 1950s, Lincoln Electric Company invented inner shield. It's sort of interesting. In Japan, the people who developed all the welding consumables were the steel companies. Kobe Steel, Nippon Steel, NKK, Kawasaki Steel, because they needed welding consumables available so they could sell their steel plate. In the United States, going back earlier, the welding consumable companies were the Union Carbides, the Aircos, the people who wanted to sell shielding gas. And they got into the welding wire business because they wanted to sell shielding gas. They make a lot more money off the shielding gas than they would off the wire, but they got into that business. Lincoln Electric was kind of an oddball because they actually started out building welding power supplies. That's why they called it Lincoln Electric. And they got into the welding wire business because they wanted to sell you the welding power supplies. And they could care less about shielding gas. They didn't sell shielding gas. So they had an incentive, whereas the other people didn't, to develop a gas metal arc process that did not require gas in a great big bottle of gas. And they developed what's called inner shield, and it's a tubular wire that has some aluminum powder on the inside. So the final deposit is about 1% aluminum. The aluminum ties up the nitrogen in the steel. If you tie up the nitrogen, you don't get the porosity. Okay, so you can weld with inner shield. The problem is you get terrible sharpies, lousy impact toughness. So anyway, it turns out inner shield, they sell inner shield electrodes that either work with straight polarity or reverse polarity. Remember, electrode negative or electrode positive. And it turns out if you run with electrode positive, you get a nice deep well deposit like this. If you run with straight polarity, you get the shallow well deposit like this. And it has to do with the other elements, the bariums and the lithiums and things they put inside that tube with the aluminum that change the arc characteristics in the plasma jet. So you get deep penetration or shallow penetration. There are times when you want shallow penetration. If you're welding on sheet metal, you just don't want to penetrate all the way through and blow a hole through your sheet metal. If you're welding on plate, you often want to get deep penetration. And you can change those things electrically, by flux, or changing the torch angle. Okay, if you've got a jet, you can soften the jet by changing the torch angle. In fact, we do that when we want to run in automatic welding very, very fast. You sometimes change the torch angle because you're getting up to high enough currents that you're just blowing things apart. And in fact, one of the problems with submerged arc welding, actually not a problem with submerged arc welding, but one of the features of submerged arc welding is that you have your electrode, and you have this bed of sand, this flux, above the plate. You have this cavity in here that the gases, or the expanding gases of the hot arc, have built this cavity, and you now have a glass slag layer, a molten glass. This process could be working at 600 or 800 amps. I've got a plasma jet that now is going to throw sparks all over everywhere. But what it does in submerged arc, anything is thrown out gets caught by this catcher's mitt of the molten glass, and the steel being heavier than molten glass, that molten steel just falls back down into the weld pool. And I remember I have a patent that I got. It was actually a very useful thing. This was the early 80s. It was about 6 months before I was coming up with a decision in the department. And there was a former professor from this department who had gone to become undersecretary of research and development and stuff. So he'd been undersecretary in Washington, and he was currently a vice president at TRW. And TRW owned a company that did stud welding. And stud welding, if you want to put a bolt, if you want to weld a bolt to a plate, you essentially just strike an arc, let it run for a second or a couple of seconds, and then push the two molten things together, and you weld the stud to the plate. If you're ever seeing by doing concrete decking on a highway, you'll see that they do these studs on there with these caps, and they cast the concrete over the studs, and it's the studs that anchor, do the mechanical interlocking with the concrete when it solidifies. Buildings, not like this, but new buildings have all these studs to anchor the concrete. They put little studs on automobiles to just hang molding on and things like that sometimes. So there's trillions, but probably billions of studs used every year, from little baby things to great big things. Well, the great big things they were interested in, this is when they were looking at the anti-ballistic missile system, and to harden the silos, they wanted to use number 13 rebar, or number 11 rebar. Number 11 rebar I mentioned before in 3371, goes in 1/8 of an inch increments. So number 11 is 1 3/8 diameter. It's a good size stud. Okay, and they wanted a fast way of welding it, because otherwise they had to have a guy go with a manual electrode and go around and it'd take a half an hour to weld every one. You got tens of thousands, if not hundreds of thousands of these things. A stud weld, on the other hand, you draw the arc and you hold it there for, at smaller studs, like a 1/2 inch in diameter, a fraction of a second, like a 1/2 second, and then you slam it together. Well, for these great big studs, you needed 2,000 or 3,000 amps. And 2,000 or 3,000 amps, the magnetic fields get so intense they actually can blow out the arc. You get sideways forces. If the current's not perfectly straight down, if the current curves the least little bit, because your electrical ground location is over here, you actually get something called magnetic arc flow, and your magnetic fields bend with the current, and the magnetic fields will blow the arc away. And so they've been trying this for supposedly for 30 years. And he calls up and says, well, can you come out and help? I'd never done stud welding before. I said, well, I don't know, why don't I come out and see? So I came out, and the first day I was there, they showed me some of the welds they had made, and it turns out with 2,000 amps, you get spatter all over everywhere. Okay? And I said, well, we need to average the current. You know, if the current's going this way and coming down and going that way, we want to kind of make it go around like this. And these are 2,000 amp arcs, and they were going for like a second and a half or so, and trying to do it, but they were getting kind of chisel points, and they couldn't get a complete weld. And I said, can we put a magnetic field around? In fact, we can just put a magnetic field by putting a loop of wire around it. You just take the welding cable, which is a DC current, you just make one loop. And if you got 2,000 amps, I now have 2,000 ampere turns of magnetic field. They said, oh yeah, we've done that. And so I said, oh, well, what's it like? They said, we'll show you. So we went, and they had a room that's about half the size of this room where they had the equipment, and they set it up, and they put the loop of the welding cable just around the stud that they were going to draw the arc. And then they had remote control, and we all got behind the door, okay, and looked in, okay? So the guy with the remote control was kind of like this, right? The rest of us kind of looked back. So they said, ready? The guy hits the remote control, and it looked like the 4th of July. The whole room lit up with sparks. Because what do? You now have a plasma jet, 2,000 amps, and it does process around because of the magnetic field, J cross B, right? Only now it's gouging. This is like carbon arc gouging. I'm melting metal and blowing it, you know, with 2,000 amp plasma jets all around the room. It was quite spectacular. And you go back and you have this huge hole, half the size of a baseball, in the plate, right? And so they kind of laughed at me. And anyway, no one took me to dinner. I was sitting at dinner that night, and I was supposed to stay the second day. And I started thinking, well, you know, that's what happens in submerged arc welding. But the difference in submerged arc is I have this black molten glass to catch it. So the next day I come in and say, you guys got any submerged arc flux? And I said, yeah, we got some. I said, well, let's go we went and made, out of a little piece of sheet metal, 16th inch sheet, we just made a little cylinder, about that big around. We put it around the stud. So I've got a stud right here. Okay, here's the stud they wanted to weld, 1 3/8 thick, or diameter. And we just put this little dam out of sheet metal. I think it took us 10 minutes to make it. You know, here's your plate you want to weld to. And we filled it up, about 2 inches deep, with submerged arc flux. And I said, no, we don't want to do this at 2,000 amps. We want to do this for 6 seconds at 800 amps. Okay? They were trying to do everything really fast at high currents. They were doing 1.5 seconds at 2,000 amps. And I said, well, let's do it at longer time, lower current, because that's going to cut down on my plasma jet. That's more like submerged arc welding. And so we go, we get behind the door, and the guy's sitting there, and one guy says, go ahead and start it. He says, I thought I hit it. There must be something wrong. And basically, after we were talking, after 6 seconds, we saw the plunger go, and the thing drops down. The thing had been running. It was so quiet. And because you had submerged arc flux, it was catching the stuff, and you couldn't even tell from 10 feet away that the arc was running. Okay? And it made a beautiful weld, a perfect weld. And then everyone went, wow, this is fantastic. And then I had we'd agreed on 5 days of consulting, and so we did some other stuff and things. But 6 months later, we filed for a patent, and I was talking to them, and they weren't very excited. And I thought, well, here we've invented a process. Now, by the way, this was a very good recommendation for this guy who was a vice president of industry, former undersecretary of defense, a former MIT full professor, because he ended up writing a letter for my tenure case, okay, because I invented a process in 2 days, right? So that it was worthwhile, even though they didn't seem very excited. I said, well, why don't you guys don't seem very excited about this. He said, well, we have a problem. We don't make any money by selling the power supplies. We make money because we know how to machine the ends on the studs to make a chisel point on the end of the stud. And we sell studs. And you've developed a process where you can just use a sheared end of the stud. So this process will basically, the reason we're patenting it is because if anyone uses it, it's going to wipe us out of business. Okay? So I said, oh, okay. So then I understood why they weren't so excited. But then about 3 years later, I was at the welding show, and I never heard anything about this process. I've heard about it twice. I was at the welding show, and there was their little booth, and they had one of these beautiful looking 1 3/8" welds sitting there on the display. And I said, well, that's an interesting weld. The guy says, oh yeah, we've got a special process for it. Really? Tell me about it. He said, oh, it's kind of proprietary. I said, you don't use a flux, do you? Oh, how'd you know that? My name's on the back. Anyway, I love to sandbag people. In any case, but that just shows some of the principles of plasma arcs and how submerged arc welding basically is kind of an interesting process because you do get spatter all over when you go to these very high currents in steel. But in this case, you use something to catch it. So actually, if you get into this, you find some of these welding processes are fairly complex. Okay? If you start figuring out all the things that are going on, which is why I have a job. Okay, any questions on any of that? If not, we're going to start heat flow in welding. And I want you to bring these notes back tomorrow. Actually, you don't have to bring them back tomorrow because I got overheads of them. But anyway. Let me give you a little of the MIT history on this. It turns out that there was a guy named Daniel Rosenthal who was Jewish, and he was living in Europe in the 1930s. And he was Jewish, and he determined around 1938 maybe Germany wasn't a good place to live. And so he first went to Holland first, I think. Anyway, he finally made it to Morocco about 1938 or 39. And he stayed there for about a year. And then while he was kind of running from the Germans, trying to get out of Europe and that part of the world, he started solving what's called the traveling point heat source solution. This is if I have a point heat source traveling on the surface of a plate, what's the temperature distribution? And it turns out it's now called the Rosenthal solution. He was not able to publish it out of Morocco. There's not that many really top-notch universities and publishing houses there. But after he got to the United States, he came to a place called MIT, and he was over in building, mechanical engineering building 2? He was over building, no, building 3, right? 3. Right across the courtyard from my office. So anyway, Rosenthal came up with the point heat source solution, traveling point heat source solution, which I'm not going to show you yet, okay? But he started out, there are whole books on solving heat flow in welding. One of the simplest is just a one-dimensional planar solution, and this would apply to a friction weld. Remember we studied friction welding, I passed around friction welds. You have two round bars that slide against each other. You've got surface heating. And so if I have 2 round bars and I have surface heating generated across that surface, it turns out the heat diffuses to either side. It's the same, Fourier's second law of heat conduction is exactly the same as Fick's second law of mass diffusion. Okay, so it turns out it's the same mathematics. It's called equation. If you solve the diffusion equation in terms of temperature, the temperature rise and temperature is a function of distance, where T0 is a reference temperature, room temperature, and this is the temperature at any point, is equal to the heat input per unit area, that's Q over A over that surface, divided by 4 pi alpha is the thermal conductivity, we'll talk about that in a little bit, times time to the 1/2 power, 1 over the density times the heat capacity. Density times heat capacity is how you change temperature to a heat. Okay, if I take that rho C sub P and put it over here, rho C sub P times temperature is equal to Q. Okay, so heat and temperature are not the same thing. They're related by rho c sub p. And then it's this is just a Gaussian exponential minus x squared times the thermal diffusivity times time. So basically, if I have a planar source of heat, I will have a Gaussian distribution of the temperature flowing away from there. And if I apply that heat for a certain amount of time, I'll have a Gaussian distribution at a longer time, T2. If I essentially instantaneously apply that heat and then turn it off, the Gaussian distribution spreads out with time. Okay? That all kind of makes sense, hopefully. For a two-dimensional heat source, I now have a line. So this one up here was friction welding, a planar heat source. For a linear heat source, that's basically the same thing as a laser or electron beam, right? I drill this deep hole and move it along the plate. Well, in this case, I'm not going to move it. But you work that out, and it's the same old thing, only now it's instead of Q over delta, and Q over A, it's Q over delta, where delta is the heat per unit length of that linear heat source. It's just a little line. As if I had a hot wire cut through butter or something. And now it's a two-dimensional Gaussian distribution. Same Gaussian, but now in terms of r squared, because I'm in axial coordinates, where r is basically just x squared plus y squared. There's the same rho c sub p. And this now has dimensions, alpha t has the dimensions of centimeters. Alpha is in centimeters squared per second, temperatures in second. So alpha t has the units of centimeters squared. Up here, alpha t to the 1/2 had units of centimeters. So I have to get rid of this. I have to end up with heat per unit area. This was heat per unit, heat per unit volume. I need heat per unit volume. And this is Q over area divided by another length dimension. So that's a heat per length cubed. This is a heat per length. And then I have to have a length squared down here. So I still have the same units. Everything's working out. And this would be similar to deep penetration laser electron beam. Oops. Here. Now, if I go to a three-dimensional heat flow with a point source solution, I'm now talking about a point. And I can do this in the center of a plate, just buried it there, or I could, by symmetry, cut off the top, and now I have a point source right on the top surface of the plate, right? If I want to cut it in two. But I'm solving it right now inside the plate. Now it's Q, it's not divided by anything, but the 4 pi alpha t becomes a 3/2, because I need length cubed. The rho c sub p is there. And now a big R, and big R is x squared plus y squared plus z squared. Okay? And now if I looked radially from there at different times, I'm going to see the same Gaussian spreading. The Gaussian heat distribution spreading out. Okay? So those are the planar, linear, and point heat source solutions for a stationary point heat source. And those are already known at the time Rosenthal was around. But what he did is he said, okay, well now I'm going to give this thing some velocity. I'm going to move the point heat source on the plate. And it turns out after Rosenthal showed how to do this point heat source, you can go back to a linear heat source, you can go back to a moving area heat source, you can do whatever you want. And Rosenthal, basically, now it's a heat, in this case, the heat input at that point source is not per unit volume anymore because we've changed the units here a little bit, so it's a little q. 2 pi k is thermal conductivity, and so my alpha t is turned into a thermal conductivity because I got rid of my heat per unit volume. 1 over r, which is the radius vector, in x squared plus y squared plus z squared square root. And now my exponential, or my Gaussian, has changed to a v over 2 alpha times r plus x, where I'm traveling in the x direction. So moving in the x direction at velocity v, q is the strength of the point heat source on the surface in dimensionless form. Well, I'm sorry, in dimensionless form it turns out to this. So Rosenthal solves that, publishes it in the Journal of Mechanical Engineering, ASME Journal, becomes famous, leaves MIT after the war, and goes out to a place called UCLA, becomes a professor of metallurgy, and writes a textbook, and he's passed away now, obviously. Anyway, if you want to look at what the Gaussian looks like in kind of 3 dimensions, like on it looks something like this, and you should have a handout of that. But it's just a skewed Gaussian, and I'll go over some of this tomorrow. But these are the isotherms looking down, going slow, faster, faster, and very fast. And we'll talk about what some of these mean. This would be a very slow process, like electroslag. This could be a slow arc process like gas tungsten arc. This could be something like gas metal arc, and this could be something like laser and electron beam. But you get distorted Gaussians distribution. So these are just isotherms looking down on top of the Gaussian. But Rosenthal was the first guy to do this. The next guy who put all this in dimensionless form was another guy who had a World War II story, Niels Christensen, who was a Norwegian freedom fighter who was skating across the mountains from Sweden to Norway to fight the Germans. And after the war, he came over here on a Fulbright fellowship to this department and to study welding, which is what he was interested in. Anyway, in 1960, in the 1960s, sometime. Anyway, that skewed Gaussian I showed you was from his paper, where he took Rosenthal's equation and put it in dimensionless form. But we can talk about that tomorrow. Okay. So all the major heat flow studies as well are done by and people at MIT.